Yes.
Yes. They staple it and give you a paper clip.
Sorry, I say what separately.
That way I don't lose anything accidentally. Oh.
I am too.
I like your sweater. I like your sweater.
Thank you.
Okay, folks, it's that time of the day. So today, our entire focus is going to be how to calculate the equilibrium constant. And we're going to do so using a variety of methods. The first one we're going to do is we're going to pick up where I left off on Monday with calculating the equilibrium constant for a reaction where we have taken that reaction and manipulated it. The second way we're going to calculate equilibrium constants is we're going to calculate the equilibrium constant from, we're going to convert between, or calculate Kp to Kc and vice versa. And then the third way we're going to calculate the equilibrium constant is we're going to calculate the equilibrium constant given concentrations at equilibrium using ice. So we're going to be calculating equilibrium constants today. Okay, so as a reminder from Monday, if we reverse a reaction, the new equilibrium constant, K prime, is going to be equal to 1 over the original equilibrium constant. If we multiply a reaction by N, then the new equilibrium constant is going to equal the original equilibrium constant raised to that multiplicative. And if we add reactions, then the new equilibrium constant is going to equal the equilibrium constant for the first reaction times the equilibrium constant for the second reaction, and we could continue. So I said I would pick up with a couple of examples. Let's look at this question here. We have carbon dioxide gas reacting with 2 hydrogen gas to form methanol. This has an equilibrium constant equal to 2.26 times 10 to the 4th. So what is the equilibrium constant for the following reactions? The first one is we're going to take and we're going to determine the equilibrium constant for methanol dissociating into carbon dioxide. That was supposed to be carbon monoxide. I apologize. It didn't balance. And 2 hydrogens. What I notice is that this is the reverse of the original reaction. Since it's the reverse of the original reaction, then my K prime is going to equal 1 over the original K. So it's going to equal 1 over 2.26 times 10 to the 4th. Or in other words, our K prime comes out to be equal to 4.425 times 10 to the negative 5. You can always think, does this make sense? And yes, it does. If the addition of carbon monoxide and hydrogen to make methanol is a extremely favorable process because it has a large equilibrium constant, then you would expect the reverse to be an unfavorable process. So it does make sense from that perspective. So let's look at the K for this reaction. What is the K for 1/2 carbon monoxide gas reacting with hydrogen gas to form 1/2 CH3OH gas? What we did is we multiplied the original equation by 1/2. So that means our K prime is going to equal the original K raised to that 1/2. Or in other words, it is 2.26 times 10 to the 4th raised to the 1/2. And so we get a value of 150.3 as our new equilibrium constant. Let's look at another example. Let's take 2 CH3OHs. Gas, and let's dissociate that into 2 carbon monoxide gas and 4 hydrogen gas. So this one is the reverse of the original reaction, and it is multiplied by 2. So our K prime is going to be equal to 1 over the K because that's the reverse. And then we're going to square it because it was multiplied by 2. So 1 over the K, which was 2.26 times 10 to the 4th, squared will equal our new equilibrium constant. And you get an equilibrium constant of 1.958 times 10 to the minus 9. Okay, let's look at one more example. Use the following reactions. And their equilibrium constants to predict the equilibrium constant. for 2A solid going to form 3D gas. Our reactions that we are working with is A solid goes to form 1/2 B gas plus C gas with a K of 0.0334, and 3D gas goes to form B gas plus 2C gas with a K2 of 2.35. First, let's figure out how we're manipulating our reactions to get the target reaction. What I notice is that I need 2A solid on the reactant side. In this first equation, I have A solid on the reactant side. So in order to get 2A solid, I'm going to have to multiply the first one by 2. So that would give me 2A solid goes to form B gas plus C gas. And the K1 prime is going to equal 0.0334 squared, or 0.00111. Now, the next thing I notice is that I need 3D on the product side. But in my second reaction, I have 3D on the reactant side. So I'm going to have to reverse the second reaction. So I'm going to have, B gas plus 2C gas going to form 3D gas. Oops, I didn't multiply my 2. And my K2 prime is going to equal 1 over 2.35 because I reversed this reaction. So it's equal to 1 divided by 2.35, which is 0.4255. Now, when we add these two reactions together, the B gas in the product side of the first reaction will cancel the B gas in the reactant side of the second equation. The 2C gas in the product side of the first equation will cancel out the 2C gas in the reactant side of the second equation. And what we're left with is 2A solid goes to form 3D gas, which is the target equation. So we added the two reactions together. According to that, our K prime is going to equal the K1 prime times the K2 prime. So our K prime is going to equal 0.0011, technically it was a 2, times 0.4255. So our K prime for this reaction is 4.76 times 10 to the minus 4. Folks, what you're doing is you are combining essentially a lesson you learned about Hess's law in College Chemistry 1, where you're manipulating reactions to add up to the overall reaction, with what we have been discussing about equilibrium constants. Questions? Yes.
One of the last ones we did, whenever you were getting it drive and it was reversed, you the 1 over whatever number it was, but you put an exponent above it.
That's because in this one up here, not only did I reverse it, but I multiplied it by 2. So I had to combine the 2 rules for reversing and multiplication.
After you were multiplying that last one.
In the last one, all I needed to do was reverse the second equation. So I didn't have to do I didn't have to do that second step because I didn't multiply the second equation by a coefficient. Other questions? Did that answer your question? Okay. Okay, so most of our conversation to this point has been about K. Specifically, we've talked about Kc, which is the equilibrium constant for concentration. And when we developed our expression, let's say we have AA plus BB going to form CC plus DD. When we developed the Kc for this, it was the concentration of C raised to the C times the concentration of D raised to the D all over the concentration of A raised to the A times the concentration of B raised to the B, where we used brackets to represent concentration. But as previously mentioned, we can talk in terms of Kp. And we use Kp a lot for gases to talk in terms of pressures. So, for example, let's go back to one of the equations we gave earlier, where we had carbon monoxide gas reacting with 2 hydrogen gas to form CH3OH gas. Instead of talking in terms of concentration, because all of these substances are gases, we can talk in terms of pressures. And we can develop the Kp for the reaction. When you develop the KP, it is developed very similarly as you would the KC. The only difference is instead of using concentration brackets, we're going to use pressure, the P, to represent pressure. So it would be the P of CH3OH over the P of CO times the P of H2 squared. We would calculate this the same way as we would calculate any other equilibrium constant, except we'd use pressures. So we're not changing how we're calculating the equilibrium constant. We're just changing what the unit is. Instead of molarity, we're talking pressure. Now, we can convert between KC and KP, and this is derived, this conversion is derived in section 15.4 of the textbook. Using the ideal gas law. Now, I am not going to spend time deriving this one. Instead, I'm just going to give you the equation. And that equation is Kp is equal to Kc times the ideal gas constant times temperature raised to the change in N. So let me identify all these parts. Kc, Kp, okay, those are equilibrium constants. In this case, the ideal gas constant is going to be 0.0821 atmosphere liters per mole Kelvin. The T is going to be our temperature in Kelvin. And the delta N stands for change in moles. Let me use the generic reaction again of AA plus BB goes to form CC plus DD to illustrate the change in moles. So our Kp would be equal to Kc times RT, and then change always means final minus initial. So it would equal, for our exponent, it would equal C plus D minus A plus B. Okay, let's look at an example. N2 gas reacts with 3H2 gas to form 2NH3 gas. This has a Kp of 6.2 times 10 to the fifth at 298 Kelvin. That's a 2. So, what is the Kc? Okay, that's gonna, then we would use the equation Kp is equal to Kc times RT delta N. It would be 6.2 times 10 to the fifth is equal to the Kp times Kc. And then we would have 0.0821 atmosphere liters per mole Kelvin times 298 Kelvin raised to 2 minus 1 plus 3. Oops. Where'd it go? Let's simplify this. So 6.2 times 10 to the fifth is equal to the Kc times 24.4658 raised to the 2 minus 4, which is a minus 2. Six 6.2 times 10 to the fifth is equal to Kc times 0.00167. So Kc equals 3.71 times 10 to the 8. Questions? Basically, all I'm doing is using the formula. To convert between Kc, Kp, yes.
So are we just getting rid of the units?
Um, Equilibrium constants don't have units. The units actually disappear because if you deal with all the units, you would wind up with molarity, which is the molarities. So Kc technically, remember, is concentration. That's molarity, which is moles per liter. So it actually cancels out the moles per liter portion of the R value, and the rate, the temperature units canceled out. So that shows you that only atmospheres are left. And since this is pressure, but you, equilibrium constants don't have units. They cancel out. Other questions? Let's look at one more example of this. Calculate the KP for iodine gas plus chlorine gas going to make 2 iodine monochloride gas with a Kc of 81.9 at 298 Kelvin. Okay, so since we want to convert between Kp and Kc, our equation is Kp is equal to Kc times RT, change in N. So our Kp is equal to 81.9 times our R, which is 0.0821 atmosphere liters per mole Kelvin, times 298 Kelvin, all raised to the power of 2 minus 2. Well, technically it's 2 minus 1 plus 1. So the Kp is equal to 81.9 times, well, 2 minus 2 is 0, and anything raised to the 0 is equal to 1. So technically this is multiplied by 1. So your Kp is also equal to 81.9. Any questions? Okay. Then what we're going to do next is we're going to calculate the equilibrium constant from measured concentrations at equilibrium. Before I get into this, we need to talk about ice or rice, depending upon who you've had before. Okay, this stands for reaction, initial concentrations, change in concentration, and equilibrium concentration. Hence the reason it's sometimes called rice. Now, we develop rice tables. So let's just, go back and get some equations here. Okay. So let's look at an example. We have carbon monoxide gas reacting with 2 hydrogen gas to form CH3OH gas. That is our reaction. Initially, our concentrations are 0.500 for the carbon monoxide, 1.00 for the hydrogen, and since this is an initial reaction, you would expect it to be 0.00 for the product. Now, for the change in reaction. According to the balanced chemical equation, you have to lose X amount of carbon monoxide. Or just to make it easier so that you'll see it later, we're going to say 1X amount because there is a 1 as the coefficient. You will lose 2X amount of the hydrogen because of the coefficient. And you will gain 1X amount of the methanol because of the coefficient. So at equilibrium, the concentration we would expect is 0.500 minus X of the carbon monoxide, 1.00 minus 2X of the hydrogen gas, and plus 1X of the methanol. Now, it was determined experimentally that the concentration of carbon monoxide at equilibrium equaled 0.15 molar. What is the Kc for this reaction? Okay. We said at equilibrium, our carbon monoxide was 0.500 minus X. That 0.500 minus X is equal to 0.15 molar. So a negative x is equal to negative 0.35 molar. X, therefore, is equal to 0.35 molar. So we can now use this information and plug it into our concentrations at equilibrium. The hydrogen concentration was equal to 1.00 minus 2x. So therefore, it is equal to 1.00 minus 2 times 0.35. Which should be 0.3. Our CH3 OH concentration at equilibrium was equal to 1 times X. So in other words, it's 1 times 0.35, or it is 0.35 molar. And in the problem we were given, the fact that our CO concentration was 0.15 molar at equilibrium. Now we can develop an equilibrium constant expression. Our Kc is going to equal the product CH3OH raised to its coefficient divided by the reactants raised to their coefficients. So CO raised to the power of 1, H2 raised to the power of 2. Plugging in our concentrations at equilibrium, it is 0.35 divided by 0.15 times 0.30 squared. Which gives you a value of 25.93. Rice tables are about to become your best friend. We are going to use them a lot over the next 2.5 chapters. So one way we can calculate the equilibrium constant is if you can figure out the concentrations of all of your species at equilibrium, then you just plug it into your equilibrium expression and solve. So thus far today, we have looked at calculating an equilibrium constant when we manipulate the equation. We reverse the equation, the equilibrium constant is 1 over the original equilibrium constant. If we multiply the equilibrium constant, the equation by some multiplicative, then it is the new equilibrium constant is equal to the original equilibrium constant raised to that multiplicative. If we add multiple reactions together, then the equilibrium constant for the summation of those reactions is equal to the equilibrium constant for the first reaction times the equilibrium constant for the second reaction, and so on. We've talked about how to convert between KC and KP to come up with a different variation on the equilibrium constant. And we have talked about how to develop the equilibrium constant using a Rice table if you know one of those concentrations of equilibrium. You just gotta know one and you can figure out everybody else. I was hoping to get to it today, but I had a feeling I wouldn't. So the first thing we're gonna do on Friday is we're gonna talk about reaction quotients. The reaction quotient is calculated the same as an equilibrium constant. But what it describes is where the reaction is with respect to equilibrium. If Q is greater than the equilibrium constant K, then the reaction is has gone to the products, has gone too far to the products. And therefore, will shift in the direction of the reactants. If Q equals K, then it is at equilibrium and it will not shift. But if Q is less than K, it means that the reaction has not reached equilibrium. And therefore, will shift towards the products. So what we're going to do first thing on Friday is we're going to calculate some reaction quotients. We're going to compare them to the equilibrium constant and determine where the reaction is with respect to equilibrium and which direction will shift. After that, we will move on to calculating concentrations at equilibrium, which will require, frequently will require the quadratic equation. And if you don't have the quadratic equation programmed into your calculator, I can get you we can talk about how to do that. And then on Monday, we will go over the Chatelier's principle, which is what your lab is about next week. Okay, I'll see you Friday. Turn it, if you did not get your lab in, make sure it's in. I have no voice.